Hello everyone. This is part 3 of topic 7, Trigonometric Substitution, and here's the last example we went over, kind of a classic example where we ended up with a sine squared, and we had to use our special power reducing double angle formulas because it was an even power of sine, and then a couple interesting things at the end of the problem where we ended up with theta and sine of 2 theta, and we had to use our inverse trig function to find theta, and then our special double angle identity to express sine of 2 theta in terms of 2 sine theta cosine theta, and then finally in algebraic form. So kind of a special example. I'm sure you'll see something similar on the exam. So we have 3 more examples left, so hopefully we'll be able to finish them in this video. And this one involves, so the directions would read, use trigonometric substitution to evaluate. Remember, you don't care what the integral looks like. You only care what the radical looks like. And you classify your a's and your u's like we always do. So a squared, the constant, 4. So a is 2. U squared, the variable. X squared, so u is x. We don't calculate the du. We go right to a right triangle, claim reference angle theta. And remember, there's always 3 things to place in the triangle: u, a, and the radical part. And based on the radical part, that decides how the triangle is constructed. And remember, the way I like to go about this is to determine what the hypotenuse is first. So the first question I always ask is, does the radical part represent the hypotenuse or one of the legs? And because it's a difference between 2 squares, it's one of the legs. And moreover, if it is one of the legs, the radical part that is, then the positive term under the radical will represent the hypotenuse. So that's x squared, so therefore u is the hypotenuse, which is x. So I'll fill that in first. And then to avoid cosecants and cotangents, make your opposite side, if the radical part is one of the legs, just always make it opposite of what theta is. And then that leaves the adjacent to be the value of a, which is 2. And then there are 2 major steps once again. You don't even have to think about the trig function you're going to define. Just force the ratio of the radical part over the constant, and then decide what trig function you're dealing with. The radical part is the opposite, the constant 2 is the adjacent, and opposite over adjacent is our tangent. So tangent of theta is that, and then we solve for the radical part, so 2 tangent theta is the radical part. Okay, then the second major step, and again, always just these 2 steps, and that leads us to the point where we can make a trigonometric substitution. And the second major step is always done this way. You don't even have to think about the trig function. You're going to force it to always be the ratio of u over a, in this case x over 2. And then with respect to theta, x is the hypotenuse, 2 is the adjacent, and that's the secant of theta, as we would expect, because remember we talked about that in the last video, where tangents and secants go together, just like sines and cosines go together. So then we solve for x, and then most importantly, after solving for x, in Roman numeral step 2, one extra step, that's to calculate the dx, because remember the whole idea is we want to be able to replace everything in this integral to be in terms of theta and trigonometric functions of theta. And of course the differential d theta, which is found by calculating the differential dx, which is the derivative of 2 secant theta, so 2 secant theta tangent theta, and then don't forget the differential d theta as well. Alright, so now we're ready for the trigonometric substitution. I always like to rewrite the original integral. You don't have to. I think it makes for a nice fluent solution. and make my substitutions. Okay, we have x to the fifth. Well, x is 2 secant of theta, but as a quantity then to the fifth. In the denominator, we have the radical part, which is 2 tangent of theta. And then the only thing left over in the integrand is the differential dx. And from Roman numeral step 2, that's 2 secant theta tangent theta with respect to theta. Okay, from there we can simplify that integral. Looks like we can cancel some 2's, cancel the tangent, and we're left with 2 to the fifth, which is 32. Let's bring that out in front. And then in total, make sure you realize there's 5 factors of secant here, coming from secant of theta to the fifth, times this factor of secant, so in total, 6 factors of secant. And then if you recall the methods for integrating powers of secants and tangents, here's an even power of secant. So to integrate an even power of secant, we borrow 2 factors. So taking away 2 factors from secant to the sixth, we're left with secant to the fourth. Those 2 factors of secant in the form of secant squared, push over with the differential d theta. Go so far as to box it off, write the word save, because the intent is for that secant squared to represent the du. Then you could look back at the cookbook recipe, but here the logical question to ask would be, if secant squared is going to represent the differential du, what is the function whose derivative gives us secant squared? And that would be tangent. So therefore, if we could change the remaining factors of secants here to tangents, we'll be able to start the u substitution process. And we can, because recall the identity, 1 plus tangent squared is secant squared. So we have 32 integral. Okay, 1 plus tangent squared theta represents 2 factors of secant, but to represent 4 of them, remember we have to square it. And so then we'll recopy the secant squared theta d theta that we're saving for our du. Alright, now we're ready for u substitution. Pick u to be the tangent of theta. And the du is secant squared theta d theta. So change of variables. Here's 1 plus u squared is the quantity squared, and identically our differential du. So 32 integral 1 plus u squared, quantity squared, differential du. Okay, we've got to square that 1 plus u squared. So if you want, take it off to the side and FOIL it. Shortcut method for squaring a binomial if you like. Remember, if it's cubed or higher, Pascal's triangle and the binomial theorem. But here, squaring, we get 1 plus 2u squared plus u to the fourth. With respect to u, 32 tags long. Now we can integrate, because we have a sum or difference of terms that are of the form u to the n. Just be careful if you had another u out in front or behind, you'd have to distribute that first, but here we can integrate. Be careful here also, integrating 1 with respect to u, we get u. Then we have plus 2 tags along, u squared integrates to be u cubed over 3, and u to the fourth integrates to be u to the fifth over 5. Close up our brackets, add our constant, and distributing the 32, we get 32u plus 64 thirds u cubed, and then plus 32 over 5 u to the fifth plus our constant. And remember, we have to write the little note where u equals, in this case it was tangent of theta, but that's not enough because you have to give that in algebraic form. So if you go back up to Roman numeral step 1, that's tangent of theta. Or if you didn't have it, as we're going to see in the next example, we'd have to go to the triangle. But tangent is the opposite, square root of x squared minus 4 over the constant 2. Okay, so let's see if we can get through the last two examples. We're at the 10-minute mark, so I think these are a little bit shorter. Okay, this one to begin with, where's the radical? Well, it's there, you just don't see it. Because you could actually rewrite this as 1 over, and then we have the square root of 4 plus x squared. That's the 1/2 power, recall. And if we cube it, we get the 3/2 power. Okay, so that's a little trick. Now, in an exam, if I gave you a situation like that, I'm always going to, you'll blatantly see the radical. Don't worry about it. Because if you didn't know that little trick, you wouldn't be able to get past. Okay, now, standard procedure, a squared, u squared. Remember, you don't care what the integral looks like. You only care about what the radical looks like. And a squared is 4, u squared, x squared, so a is 2, and u is x. Immediately do our right triangle, reference angle theta, and look at the radical and ask, is it the hypotenuse or one of the legs? And because it's a sum of two squares, it is the hypotenuse. And so we'll label our legs as our u and our a, or the x and the 2. And in this case, it's convenient to make the choice of u opposite of theta. Okay, now for the two major steps. Remember, you don't care about the trig function you're defining. You just simply force the ratio in Roman numeral step 1 of the radical part over the constant. Then with respect to the radical part, or with respect to theta, excuse me, the radical part's the hypotenuse, the constant is the adjacent, so that's the secant of theta. And then we go to Roman numeral step 2. Oops, before we do that, let's solve for the radical. So 2 secant theta is the radical part. Okay, Roman numeral step 2, again, don't even think about the trig function, just force the ratio of u over a, in this case x over 2, x is opposite, 2 is the adjacent, and there's the tangent of theta, as we would expect, right? Because secants, tangents go together. Solve for x is 2 tangent theta, and most importantly, the differential dx. And the derivative of tangent, secant squared, so 2 secant squared theta, and formally the differential d theta as well. Alright, so now we're ready for a trigonometric substitution. I'll rewrite this in the form where we expressed it as a radical being cubed. Alright, so there's really only two things to substitute. We have 1 over, and then the radical from Roman numeral step 1 is 2 secant of theta, but that needs to be cubed. And then we have times 2 secant squared theta d theta is the differential dx. And simplifying that, well, we got, this is 2 cubed, so that's 8, but 2 over 8 is 1/4. And then the integral, there's 2 secants, 2 factors of secant in the numerator. There's 3 factors of secant in the denominator. So canceling 2, we get 1 over secant. Okay, which is not a standard form, but here's the thing, you may need identities on occasion. So basic trig identity, recall 1 over secant is cosine. So the reciprocal of secant is cosine. So 1/4 cosine theta d theta. And cosine integrates to be the sine of theta. Now we have to give this an algebraic term, so here's the thing. If you look back at Roman numeral step 1 and 2, everything we've seen up until this point, whatever trig function we ended up with in our answer, was contained in Roman numeral steps 1 or 2. Here it is not. So all you have to do is just simply go back to the triangle, because the triangle defines any trig function. Sine of theta is the opposite, which is x, over the hypotenuse, that radical part. So it looks like we have x over, and then 4, and the radical part. Okay, so final example. We're at the 15-minute mark, so I think we'll squeeze it in here safely. Again, you don't care what the integral looks like. You only care about the radical. Claim your a's and u's. So a squared 9, u squared 4x squared. Remember, never negative. The negative tells us how we're going to place the UA and the radical in the triangle. So we have that a is 3, u is 2x. Question is, who's the hypotenuse? Is it the radical part? And the answer would be no, because it's a difference, so we know the radical part's a leg. And if the radical part is a leg, remember it's always the first term under the radical that represents the hypotenuse. The square root of that, of course. So a is the hypotenuse, that's 3. Here it really doesn't matter where you put the radical and where you put your u. But just to be consistent, I'm going to suggest making the radical part always opposite of theta. Okay, now the two major steps. Roman numeral step 1. Again, don't even think about it. Just force the ratio of the radical over the constant. And with respect to theta, the radical is the opposite. Constant's the hypotenuse. That's the sine of theta. And solve for the radical part. So 3 sine theta is the radical part. And then guess what trig function is going to be generated here? Well, if it's sine here, we'd expect a cosine. Let's see. Remember, you always just force u over a, in this case 2x over 3. 2x is adjacent, 3 the hypotenuse, and as expected, there's a cosine. Okay, solve for x, so multiply by 3 halves most efficiently. So 3 halves cosine theta is x, and then most importantly, differential dx. So that's 3 halves minus, this is the derivative of cosine minus sine, so minus 3 halves sine theta, and formally the d theta as well. Okay, so now we're ready for complete trigonometric substitution. We have 1 over x squared, the radical part, and the differential. So x squared. Well, x is 3 halves cosine theta. That'll need to be squared. The radical part is 3 sine of theta. We have 1 over all of that times the differential dx, which was negative 3 halves sine theta d theta. Okay, so now we need to clean some things up. Well, we can cancel the signs, and I don't know how you want to deal with the coefficients. I'm going to say off to the side here and do the work on the coefficients. I've got a negative 3 halves over a 3 halves that's being squared times a 3. So there's the negative 3 halves in the numerator. There's the 3 halves being squared and times a 3. If you're really clever, you can cancel 1 factor of 3 halves out and work it out from there. But by brute force, you can get this, let's say minus 3 halves over, that'd be 9 fourths times 3, 27 fourths. So minus 3/2 times 4 over 27. Cancel 1, 2, 9, and negative 1. So it looks like negative 2/9. Okay, so that's probably the part that people will make mistakes on. Not the calculus. The calculus is easy. It's the 5th grade arithmetic. Okay, so we have negative 2/9. And then the integral of, here's the substance. What do we have left? Well, it looks like just this cosine in the denominator that's squared. And 1 over cosine squared theta. Okay, again, you might need identities. Okay, sometimes just the basic reciprocal identities. Sometimes you'll have to actually change everything to sines and cosines. That's a hint for the exam. But here, 1 over cosine is secant. And therefore, 1 over cosine squared is secant squared theta. And secant squared integrates to be the tangent of theta. Okay, but here's the thing again. Tangent of theta is not in Roman numeral steps 1 or 2. So just use the definition of tangent in terms of the sides of the trig functions. So we have minus 2/9 times opposite, the radical part, over the adjacent 2x, and then plus the constant. So then we'll cancel out a 2. So we get negative 1/9, and oops, almost lost that x in the denominator. So let me do it this way. Let me say 9x in the denominator, and then minus that radical in the numerator. Alright, so sorry about that. There you go. Okay, so that's it. That's the end of trigonometric substitution. Next time, topic 8, partial fractions. It'll take more than a few lessons. Usually takes 3 days to get through partial fractions, so I expect 4 or 5 parts for that. So I'll keep updating Blackboard with daily assignments, and we'll see you next time.